LeetCode problem 4. Median of two sorted arrays. Sounds simple, but the stakes are real. This isn't just about merging arrays. It's the kind of thing real-time analytics engines, financial systems, and distributed databases wrestle with every second. Finding a median fast can be mission critical. But here's the twist. We need big O of log of m plus n. Tight constraints. Let's break it down, starting simple, then gliding into something faster. All right, ducklings, time to waddle into our first approach. Brute force. It's basic, but works. A steady, step-by-step march through the problem. Let's drop into the code and see how it holds up. First move, we create a new array big enough to fit both inputs. That gives us a workspace to merge the elements before calculating the median. We toss in all the elements from the first array, then follow with the second. Now we've got everything in one place, just not in order yet. Since both arrays came in sorted but were never merged, we need to sort the combined array. That's key for lining up the values to locate the true median. Once sorted, we check the total number of elements. This lets us know where the median should sit, or how to average two middle values. If that total count is even, we grab the two center elements and take their average. That gives us the midpoint value we're after. Otherwise, for an odd count, the median is just the center element, no averaging needed. This takes big O of m plus n log of m plus n time due to the sort, around 22,000 steps max. Space is also big O of m plus n, since we're holding all the elements again. It's clean, but definitely not duck speed for large arrays. So how do we avoid all that sorting? Let's think smarter. What if we only tracked the values we need to find the median and skipped the rest? Let's dive into that next idea. We begin by storing the lengths of both arrays and calculating the total combined length. That tells us exactly how far we need to simulate a merge. Then, we set two pointers, one for each array, and two variables to track the current and previous elements. These act as our median candidates as we go. Now we simulate merging the arrays, but stop halfway. Since the median lives near the center, we don't need to process the full list. On each pass, we update the previous and current values. This gives us a sliding window to catch the median once we reach the target index. To keep our merge in sorted order, we always pick the smaller of the two current elements. If one array runs out, we pull from the other. Clean and consistent. Once we're done, we check if the total count is even. If so, we return the average of our last two tracked values. That's our median. If the total is odd, we just return the current value. That's the middle of the merged stream. This method cuts the time to big O of half of m plus n, so only about 1,000 comparisons. And space drops to big O of 1, no extra arrays, just a couple of variables. Much leaner. But even with that, we're still doing a linear scan up to the middle. We can do better. What if we skipped the scan entirely and binary searched our way to the median? Let's shift to that. To do this cleanly, we always binary search on the smaller array. That keeps the index math safe and avoids boundary bugs. With that, we grab the lengths of both arrays and set our binary search range inside the smaller one. The goal? Find the perfect partition point. Inside our loop, we keep narrowing that range, adjusting the partition until the left and right sides line up just right. We calculate the cut position in the smaller array, then use it to compute the cut in the larger one, ensuring both sides of the combined array balance correctly. At the partition edge, we pull out values to the left and right. If we run out on either side, we simulate extremes like negative or positive infinity to keep our comparisons safe. We do the same with the larger array, grabbing edge values or simulating limits where needed. This keeps our math stable across cases. Now comes the check. If the max of the lefts is less than or equal to the min of the rights, we've found the perfect split. That's our golden partition. If the total count is even, the median is the average of the max left and min right, exactly the two values straddling the split. But if the total is odd, we return the max of the left side. That's the one value sitting in the middle. If the left side is too big, It means we need to move our cut left, so we slide the high pointer back and try again. Otherwise, if the cut's too far left, we nudge the low pointer right to balance things out. This final check is a fallback. It handles cases where inputs don't allow a clean partition. Shouldn't happen with valid data, but good to cover. This approach runs in big O of log of the smaller array's length, meaning just 10 steps for 1,000 elements. Space stays constant at big O of 1. That's blazing fast and scales like a champ. We started with brute force, reliable but heavy. Then we shed extra work with a simulated merge, lighter but still linear. Finally, we brought out binary search, precise, elegant, and lightning fast. That's the tool top interviewers look for, the one that shows you think in trade-offs. This isn't just a LeetCode problem. It's a pattern you'll use in any high-performance system where speed and balance matter. So ask yourself, where else can you slice the search space this way? Keep exploring, keep optimizing, and as always, keep quacking toward better solutions.